Good morning, students. In today's class, we'll just discuss the other topic, which is related to ferroelectrics and shearing bridge method. Right. So, in detail, we are going to study about this particular phenomenon. Right. So, what we have completed in the last class, we started with this. We started with the dielectrics. What are dielectrics? So dielectrics are nothing but the materials in which the electrons are tightly bonded. So what is actually dipole? So dipole, when we come to the electric dipole, so the two charges, opposite charges, when they are separated by a small distance, we call such such material as such definition in which the two charges are separated, equal and opposite charges are separated by a small distance. We just call that as electric dipole. Now, what is dipole moment? We discussed that it is the product of the magnitude of the charges and the distance between them, and which is related by the mathematical equation mu suffix c is equal to q into x. So the examples what we have taken mica, glass, and so on. So when we see symmetrically dielectric atom, so when a dielectric material is placed between the two parallel plate capacitors, it looks like this. And when we talk about the presence of electric field, so definitely there is a separation of charges. With the separation of charges, we just call this is polarization. Now, in order to understand the characteristic of the dielectric material, we need to understand some important parameters. The first important parameter that we need to remember is dielectric constant. So the characteristic of a dielectric material can be known by dielectric constant, which is given by epsilon r is equal to epsilon by epsilon naught. That is the ratio of permittivity of the medium to the permittivity of the free space. Then we move forward. What is actually mean electric polarization? So the producing of the electric dipoles in the presence of an electric field, we just say that is called polarization in dielectrics. So in a normal and comfortable language, if we say that the separation between the charges, it is also said to be a correct definition of dielectric electric polarization. Now, when we just move forward, we just discuss about polarizability. Now, polarizability is a mathematical parameter which gives us the information regarding the exact polarizability, the ability of the charges to get separated from one another. So that is mathematically given as mu. That is mu is directly proportional to E. So this mu is nothing but the induced dipole moment is directly proportional to the intensity, strength of the, or we just say intensity of the electric field. So when I just remove this proportionality constant, mu is equal to alpha E, where alpha is the probability constant. This particular aspect that we discussed in the last class, and we just we need to understand what is electric flux density, and we got a mathematical value. What is electric flux density? The amount of charge per unit area. We just say that the amount of electric charge per unit area is nothing but electric flux density, and which is mathematically given as T is equal to epsilon E plus P. And we had derived the susceptibility. So electric susceptibility, the susceptibility value will give us the information about the ability of the dielectric material or the ability of the medium to get right polar. So the capacity, or we can just say that the capacity of the medium to hold the amount of intensity of the electric field of so we just say that is called electric susceptibility. And that electric susceptibility is given by zeta E is equal to epsilon r minus 1. We have just seen that. And then we move forward to the different polarization which is taking place at different, what you can say, it may be solid, liquid, or gases. So in different forms, the various processes by which the polarization of the charges are taking place, that may be electronic polarization, ionic orientation polarization, and space charge polarization. So we have given our due importance to the last classes to electronic polarization. So how to define this electronic polarization? So we have taken a dielectric atom. So when an electric field is applied to a dielectric atom, positive charge nucleus displaces is separated in the direction of the applied electric field, and the electron cloud will be separated in the opposite direction to the positive charge nucleus. And this kind of displacement, we say that is called the electric, we just say that is called electronic polarization. So now this is the parameter we discussed in the last class, that mu suffix c is equal to alpha E into EV. Why we have written suffix E? Here we are talking about the electronic polarizability. Now this particular value will give us the electronic polarizability. Alpha suffix E is equal to E by mu E. So you already know what is mu E. Mu suffix E is nothing but Q into X, right? That is the induced dipole moment, or dipole moment is given by the product of magnitude of the charge and the separation between the charges, right? Now we had where actually this particular electronic polarization is taking place, in which type of, when we talk about gases, so it will be mostly in the monoatomic gases. And when we talk about solid, it may be diamond and phosphorus. It may occur in the solid materials. Now, when we just move to the next important aspect, how this particular dielectric electronic polarizability occurs at what type of frequency range. So we just had an answer that it occurs at the optical frequencies, that is 10 power 15 hertz, and it doesn't depend upon the temperature. So this electronic polarizability is independent of the temperature. As we have moved forward, so we just discuss about the expression of electronic polarization. So with the no man's land, we have to get the exact expression, how to calculate the electronic polarizability of this monoatomic gases, or the solid like diamond, phosphorus, and so on. So in order to have an expression, what we need to consider is that we have just considered a dielectric atom when it is placed in an electric field. So the nucleus is, let us consider the charge of the nucleus is considered to be plus Ze, and the electron cloud is considered to be having the charge as minus Ze, and the force which is acting on this what you can say a positive charge and a negative charge. Let us consider in a dielectric atom. It has been invented by Lorentz. So that type of the internal field which is existing inside the dielectric atom is known as Lorentz field or internal field. We just say that is called Lorentz force. Now the definitely when we talk about the electric field, we already know that when you apply an electric field to a dielectric atom or dielectric substance, what will happen? The separation of charges, polarization is taking place. So how much the charges are separated until you find that there is an attractive Coulombic force which will balance the Lorentz force. Now this attractive force and the Lorentz will make the equilibrium state of the dielectric atom, and now we can just imagine the atom is nothing but it is in the shape of a sphere, and the electron cloud, you can say there is another sphere. The atom is having a radius, since the dielectric atom is a sphere, which is having a radius capital R, and the electron cloud is also a sphere, and it will have a radius as capital X. The small black dots, whatever you are seeing on the schematic diagram, they are nothing but one is the nucleus and another is the electron cloud, which is separated when you apply the electric field. You can see this is the case for the presence of the field, and this is the case of the dielectric atom when there is no electric field. Clear, everybody? Now, so when we just derive the expression on how we need to understand that what actually we need to proceed forward. So we have just taken the charge density of the sphere. So how to calculate charge density of the sphere? That is given by the total charge which is distributed inside the sphere, that is minus Ze by the volume of the sphere 4 by 3 pi r cube. Now here we need to understand minus Ze represent the total charge in the sphere. So now then we just move forward that the electron cloud which is there in the dielectric atom. See, so it is having a radius small x. So the atom is having a charge, right? So this charge is nothing but it is given by the product of the charge density and the volume of the electron cloud. So the charge density just now we calculated in the here. So we just substitute that value here, and the volume of the what you can say electron cloud is nothing but 4 pi 3 pi x cube, right? So here 4 pi 3 pi 4 pi 3 will get cancelled, So now we obtain that the negative charge in the sphere having the radius x, that is the electron charge, that is given by minus z e by capital R cube into x cube. Now, since this is the case when there is an Lorentz force, right? We have just calculated what with respect to the Lorentz force. Now, I already told you there is an existence of Coulombic force. So what is the basic formula, mathematical formula of Coulombic force? That is given by 1 by 4 pi epsilon naught QE into QP by x square. So that is equal to 1 by 4 pi epsilon naught x square into minus ZE x cube by R cube into ZE. So QE we just calculated here. The QE value, you can see QE value is minus ZE capital R cube into x cube. So QE, instead of this QE, I have written this 1 by 4 pi epsilon naught x square, 1 by 4 pi epsilon naught x square we have written. QP is what? That is the charge that is given by the charge of the nucleus, that is ZE. So when you just multiply this, you will obtain this particular equation. Now this is the equation for the Coulombic force. This is equation 1 and this is equation number 2. So as we move forward, we equated and we got the electronic polarizability value as 4 pi epsilon naught R cube. Now this is the way how we have calculated the electronic polarizability in the last class. So as we move to the next topic, that is how, see, now we had an example of electronic polarization both in the solid and gases. Now when I say ionic polarization, you can just imagine that we are talking about the atom. See, what is ions actually? Ions are nothing but they are they are residing in the atoms. And how what is the basic difference between the atom and the ions, right? So what is that ions? Ions are nothing but in which the electrons, either the electrons deficiency will be there, or you will find that their electrons are more. So if this is the case, then we say that is called ion. So that is what we understand, right, in with the previous knowledge. Now, the ionic polarization occurs when the atoms form molecules, and it's mainly due to the relative displacement of atom. You can see it is formed. It is due to the displacement of the atoms. So atoms have been displaced, and here when the atoms are displaced, definitely there will be change in the values of the electrons. Either the electrons will be more or the electrons will be less, and which is represented with plus or minus sign. So now this displacement is occurring in the presence, again, in the presence of the electric field. So the ionic polarization, if we just define the ionic polarization, the ionic polarization occurs when an electric field is applied to a dielectric atom. What will happen is that there will be displacement of the ions, and that displacement I will just show you with this simple figure. Let us consider there is a cation, and when we talk about NaCl, right? We just now when we talk about generally ion, so the first example that comes into my mind is NaCl. So when NaCl is in the presence of the electric field, what will happen is the cation and the anion displaced. So this is shown by this schematic diagram. So you can see this this such type of polarization is known as the ionic polarization, and this will be occurring in the NaCl, KCl, and so on. This is examples of the potassium chloride or sodium chloride. They are the examples in which the ionic polarization occurs. Now, this polarization occurs when we talk about frequency range. It occurs at 10 power 15, 13 hertz. So when we compare the polarization occurs, that is 10 power 15 hertz. In the case of the electronic polarization, that comes under optical frequency. Here you can see this type of frequency range is 10 power 13 hertz, will come under infrared radiation. Now this is a slower process when compared to the electronic polarization, and definitely this is also not dependent on the temperature. This the definition you require. So for you in the syllabus, you need not remember all these equations, right? And so you just, if you know what is actually the meaning of the ionic polarization and how this ionic polarization will occur at a different frequency, that part you need to remember. So this part is very, very important here. So the electronic polarization when compared to the ionic polarization is greater when compared to the ionic. Electronic polarization is somewhat a process which is higher than the ionic polarization. And definitely it is also independent of temperature. When we move forward to the orientation polarization, where actually orientation, what is actually orientation polarization. Here we talk about molecules. So it is also called, the orientation polarization is also known as dipolar or the molecular polarization. The molecules such as hydrogen, nitrogen, oxygen, chlorine, and so on, methane, and etc., does not carry any dipole because the center of the positive charge and the center of the negative charge coincide. So on the other hand, see, you already know from this is the chemistry, what you can say, a chemistry part. What is the definition of the non-polar molecule? Just now I told you about the non-polar molecules where the center of positive charge and the center of negative charge are coinciding. So on the other hand, molecules like this CH3, Cl and H2O and Cl, they are called polar molecules, which carries the dipoles in the absence of the electric field. We just say this is called polar molecules. These non-polar and polar molecules exist inside the dielectric materials. So if if the positive charge and the center of the negative charge is coinciding, we just say that is called the non-polar molecules. If they are not coinciding, we just say that is called polar molecules. So now the polar molecules example is this H2OCl, and the non-polar molecules is H2N2. So what is the important? Why we need to understand this polar and non-polar molecules? You can just see that it depends. Now it refers to dipole moment. However, the net dipole moment is negligible since all the molecular dipoles are oriented randomly when there is no electric field. So in the presence of the electric field, these all dipoles orient themselves in the direction of the field. As a result, the net dipole moment becomes enormous. Now, see, we need to understand this polar and non-polar molecules phenomena when it comes to the orientation polarization. See, the orientation polarization will occur in this type of elements where you'll find that when you don't apply an electric field to these elements, definitely these dipoles are not they are oriented randomly. So and if electric field is applied, then they will be oriented in a direction of the field the same way. So this is called orientation polarization, and definitely it occurs at the frequency range of 10 to the power of 6. See, for an engineering student, you need to understand what is the definition, at what frequency range this type of polarization is occurring, and is it depending upon the temperature or not. So now it occurs at the frequency of 10 to the power of 6 hertz to 10 to the power of 10 hertz. So now these are the smaller frequencies. So and these smaller frequencies, we just say that is they are they are dependent on the temperature. This is a very important aspect, that the orientation polarization when compared to ionic and the electronic polarization is actually dependent on the temperature. When we consider in the case of electronic and ionic polarization, they are not dependent. Now, we see when we move, so this type of space charge polarization is another important aspect. So that is also a type of polarization which occurs at lower frequencies. Now that is also dependent upon the temperature. Now we just say that is called power frequencies. So okay, now when we move to the next important aspect of see here. Now no, this is what we require in today's class. This is important aspect. So in this class, actually, how to measure the capacitance of the capacitor. That is called shearing bridge method. This is a shearing bridge method by which we can calculate the capacitance of the capacitor. Now, just now I told you the dielectric material. In dielectric material, we had a dielectric constant. The dielectric constant will give us the information regarding the character of the dielectric material. So by shearing bridge method, we can know the capacitance of the capacitor by using the what you can say Wheatstone bridge type of phenomena here. So what is our aim? Our aim is to find out the capacitance, unknown capacitance. This is R1. We are actually finding out the capacitance, right? This value, capacitance of this capacitor. Now, in order to understand this particular aspect, first of all, you need to understand this figure, right? So in the intermediate class, you had information regarding these Wheatstone bridge, right? So PQRS, right? In this particular type, the same thing we are having. We are having the how many capacitance? C1, C2, C4, 3 capacitance and 3 resistance. So you see, please don't get confused that I have written here C1 and C2 and here there is a C4. This is only for the reference purpose. If you want, you can just write C1, C2, C3 here. If you want, you can write R1, R2, R3. This is only for the what you can say for our comfortable calculation. So you can just write it down as C1, C2, C3. Here also you can write R1, R2, R3. Your wish, right? It depends. See, the representation part you can write, right? So now this is the way how we need to calculate the capacitance of the capacitor by means of, there are different methods, right? And so we want to find out the capacitance of the capacitor. So how we are calculating? First of all, what are the terms which are included here? Here D is nothing but null detector, that is the galvanometer as in the case of the Wheatstone bridge. So here you are having a low voltage, we can say frequency oscillator, and this symbol indicates a frequency oscillator. Now when we move to this figure, you can see this is what is this this is E1, E2, E3, E4, I1, I2, I3, and 4. That are nothing but the voltages and the currents which are flowing inside this particular circuit. Right now, this is the exactly what is actually what in the figure we are just now. Let us consider the capacitor C1, whose capacitance is to be defined. You can see we are calculating the capacitance of the C1, right? Clearly. So R1 is a series resistance representing the amount of loss. See, R1 is the loss uh, loss capacitance. Is the series resistance which are representing the loss of capacitance, right? So this C1 and R1 are in series with each other. This C4 and R4 are in parallel with each other. So we need to understand what is a C2 here. C2 is a standard capacitance. Standard capacitance means what? The capacitor which is free from NVX. R3 is a non-inductive resistance, right? And C4 is a variable capacitor, and R4 is also a non-inductive resistance which is parallel with the variable capacitor C4. So when the bridge is balanced condition, you already know when the bridge will be balanced for Wheatstone. So at zero current passes through the null detector. See, which null detectors, or else you can just have a galvanometer where it show the null deflection. It shows that the potential across the null detector is zero at which condition, at this balance condition. So instead of that P by Q is equal to R by S, we are just representing that with the Z1 and Z2. See, you need to remember this. See what this resembles actually. This is what, instead of P by Q, as in the case of your what you can say Wheatstone bridge, the same thing we are doing here, but with different representation. Everything is same, right? So R by yes. So here, yeah, I said that P1, P is nothing but Z1, right? This is only representation, right? Z3 is your R, Z4 is your S. That's all what we are doing in this particular phenomenon. So here, instead of P by Q is equal to R by S, this is Z1 by Z2 is equal to Z3 by Z4. Now, this is also a type of representation. Now, Z1 into Z4. Why, sir? Why we just Z we represent, that is called the internal impedance, right? So, any circuit, as you have known to the, you just had information in the basic electrical engineering subject that we, right? There is internal resistance, or we just say that internal resistance is an impedance. So instead of writing the resistance value, we are just writing the impedance value. Z1 by Z2 is equal to Z3 by Z4. So I just multiply this Z1 into Z4 is equal to Z2 into Z3. So or else I can just write it as a P Z1. So P Z1 is P. What is Z4 here? S P S is equal to, you can just see, 2 is right, Q into R. Right. So now this is Z1, Z4 is equal to Q. Now the same way what we are doing in the, see, and I think that you got a clear understanding what actually we are doing, right? Okay. Now, so here we are just writing the R1 and the capacitance. This is the reactive capacitance, which is given by the reactive capacitance is given by 1 by j omega C1. This is a representation. You can just refer this with your VWD solve also. So this is the reactive capacitance, which is given by 1 by j. When they are series, C capacitance is series with the resistance, we can just represent it with R1 plus 1 by j omega C1, right? Right, and R4 by 1 plus j omega C4 R4 is equal to 1 by j omega C2 into R3. Now, this particular aspect we have written with respect to the reactive capacitance. So, considering that, multiply it and you get this particular value. Right, just simply by means of simple mathematical what you can say calculation. So we just got this value. Now you can just say j is there. So j is an imaginary part, and the part which is not having j is a real part. So when you equate this real part, first of all, so we can see r1 and here r3 r4 c4 by c2. So r1 r4 get cancelled. R1 is equal to r3 c4 by C2. This is equation number 1. Now, when you equate this imaginary part, we'll get C1 is equal to C2 into R4 by R3. Now, this is the capacitance value that we have obtained by using this shearing bridge apparatus. So again, you will have definitely a doubt, sir, how we got 1 by j omega C1 and how we have written this R4 by 1 plus j omega C4 R4. So when we just consider this particular see the diagram, when you see the diagram, when they are in series, the reactive capacitance here can be written as 1 by j omega C1. This you need to understand. 1 by j omega C1 here. They are parallel, then definitely it will be into, right? You don't write 1 by j omega, just write j omega C4 and R for 1 plus j omega C4 R4. So in that particular manner, we have just written this values, and we got this values as R1 is this one and RC1 imaginary real and imaginary part. With this, we will calculate the shearing bridge by means of shearing bridge apparatus. We are calculating the unknown resistance, unknown capacitance of the given capacitor, as we have seen. Now, this is about the shearing bridge apparatus. The what you can say that as we move on to our next one, right? So, what is actually the meaning of ferroelectrics? Now, ferroelectric materials or ferroelectricity is the ferroelectric crystals are exhibiting a polarization. So, what type of polarization they are exhibiting? That is called electric polarization. Without application of the electric field, some crystals are exhibiting spontaneous polarization. Now, and these crystals which are exhibiting the spontaneous polarization, we say that is called ferroelectric material, or this phenomena is known as ferroelectricity. Now, this part is very, very important to understand. Why? Because these ferroelectric materials will be used in your hard disks, right? Instead of magnetic hard disks, we use the nowadays we are trying to scientists are trying to introduce the ferroelectric materials, right? So that is what how this related to your CS computer science engineering students. So just now I told you that the instead of your magnetic hard disk, the scientists are trying to just introduce these ferroelectric materials. Now, why it is happening and what is the application? I will show you the exact video for this in order to understand this particular ferroelectricity. So in the next class, we'll just discuss about the ferroelectricity and the example. See, these two topics are remaining in the syllabus now: ferroelectric material and the barium titanate. This is one of the example of ferroelectric materials, barium titanate, and also sodium brucella. These are a few examples, but for the now in the syllabus, the ferroelectric, what is actually meaning of ferroelectricity, ferroelectric material, and and we just discuss in detail about the ferroelectric material, that is barium titanate. We'll just take a barium titanate, and that we'll be discussing in our next class. Right. For now, thank you, everyone. Thank you for your patience. We just in today's class, we just we'll end our today's class. Thank you, everyone. Thank you for your patience.